My name is David Holliday. I work on the Azure gaming team, so we have a new team that's dedicated to gaming workloads running in the cloud. And I'm just going to take a couple minutes here at the beginning just to orient a couple things that we have at the show that I want you to be aware of that have to do with building mobile games that are cloud connected. And then I'll introduce my good friend Kali, and then he'll take it from there to go through his actual game and how he's built with Azure. So just to start, how many of you have visited down at the Azure booth so far? Yes? Okay, anybody get a controller? Yes, so we have a presence down there, a number of different topics. There's a lot of things that we have for helping build games, developing faster, scaling it out globally, helping to monetize. And those are the topics that we have in the booth this year. And specifically, we want to concentrate on building mobile games, so iOS and Android games, as well as across all different platforms like Nintendo Switch, PS4, Xbox, PC. So we're cloud agnostic to the device. There's a number of topics if you go down to our booth there to talk about. I want to call out just a couple. PlayFab is an acquisition that we've just done recently. They have a set of live ops tools for being able to enable a game for monetization, player retention, and things like that. There's a super exciting set of tools that they have to enable those. And we have a special here that I'll talk about in just a second. We also have something that's called App Center, and App Center is focused around if you want to build and test and deploy and debug and get crash analytics and things like that around mobile games. We have a focus for that as well. Then we also have folks from Visual Studio that are down there. If you're building with Unity, etc., you can chat with them. We have some of our mixed reality headsets that are down there you can try out. We also have Mixer there and the Xbox folks and a number of other things that are happening at the booth. So if you're looking for some of the topics that I'm going to bring up and you want to find an expert, we have some down at the booth. Now, one of the things I want to call out is that we have a special offer that we're just offering here. And the goal of this offer is we want to really help those who want to create mobile games with a set of tools. And this is a limited offer that we're putting out here. It's basically $2,500 worth of gaming services that we're giving away free. And that is PlayFab has a SKU that's called an indie SKU. You normally would pay $99 a month for that SKU. We're going to give that away free for a year, as well as App Center. So App Center has this testing capability. Well, we have actually like 3,300 different mobile devices that are out in the cloud. And so obviously testing across different devices becomes a big issue. And so this App Center SKU lets you test across these devices in the cloud instead of setting your own devices up like that. That's normally a $99 a month SKU as well. So we're going to give that away free for a year. And then we have a tier of Azure services that are free in there as well. So this is limited to the first 1,000 signups. So I wanted to call your attention to that. If you want to get this, I would jump on that URL at the top, aka.ms/GDC offer. And using the distribution capabilities of mobile games and the App Center testing and then the PlayFab Live Ops services, this is really targeted at those who want to create a mobile game for iOS and Android. So please jump on that if you want to. We'll cut that off when we get to 1,000 people signed up for that. And then one last thing I want to call out that's super interesting if you're building a game is this new handbook that we've just created, which is the PlayFab's Guide to Live Ops. So it introduces what Live Ops concepts are. Then it actually goes into techniques for Live Ops, like how to do Live Ops basically, and then how PlayFab tools and services map to that. So the idea of Live Ops, really is that the way games are created is more like a service now, and the monetization and the lifespan of those is continuous. It's not just going to buy a disc and you play it and throw it away. It's like evolves and constantly gets updated. You retain, retention with your gamers that are out there. You can do, targeted monetization. You can do analytics to find out what's going on in the game and what you need to tweak and respond to. And it's just this feedback loop. And what we found is when we look at this, those who create a mobile game without Live Ops, they can have a good launch, and then it kind of tapers off. But a lot of folks, when you take the techniques in this manual, will start with a minimum viable product, and they'll add live ops to it, and you'll just see this, arc that goes up as far as the retention, the monetization, how much dollars that they make. So this is a very useful guide. So when you're thinking about building a mobile game, this live ops handbook is down there. So if you want to just go to the booth, you can grab a copy of this. We'll also stick this online as a PDF later, post the show. So I want to make you aware of just those couple tools if you're into creating mobile games that we have. And please visit us down at the Azure booth if you're interested in that, and people will be happy to give you a demo of everything that I've talked about here. So with that, let me stop there, and what I'd like to do is introduce Kylie from Next Game, and he'll talk through his experience with building a game.
Thank you.
The clicker wasn't working.
Hello, everybody. Glad to be here. So, first a little bit of me, and then I'll tell a little bit about Next Games in general, and then I'll delve into how we build the backend for our games and what were the lessons we learned there. So, I'm the CTO of the company. I'm as much as a game developer as a try to do all the CTO stuff, which mainly is the technology decisions and talking a lot how we build our backend and our architecture in general, and how we structure our games. So to quickly go through what is Next Games all about. So we're a Finnish-based gaming company. We do mobile games that are free to play. We have launched 2 games. Our first game was Compass Point West, which was based on our own IP. And then quite shortly after that, we launched our second game, which was the No Man's Land, The Walking Dead No Man's Land, that is based on the TV series, which you probably most of know of. Recently, maybe to highlight something, we were the first gaming company to go public in Finland, so that was a big milestone for us. Obviously, our biggest game is The Walking Dead No Man's Land, and this talk is very much about how we build the technology that drives it. We have approximately almost 500,000 unique players each day accessing the game. We generate quite a lot of data each day because we log basically every movement and every action that the players do, so that generates around 120 gigabytes worth of data. We sort of bombard the database because of that. So on a peak days, we can have up to 11,500 database requests per second. And within our game, we kill around 43 million walkers per day, so we can get through US in about 2 weeks. So then we would have killed everybody in the US who have turned into walkers in the TV series. So yeah, to tell more about like how we build everything, here's a picture of our high-level architecture. I don't know how many of you actually is a server developer on a game team, and how many of you are just developers in general. All the rest, great. So I know how to adjust the talk. So what we did in order to build our backend, we choose to do a very generic approach, and here you can see sort of like what are the tools that we use there. For example, for load balancing, in order to make sure that we always catch the fastest server, we use the traffic manager, which is an Azure service, and also cloud services themselves have a specific own load balancing. For our front servers, which is the part that actually runs the game logic on, we use cloud services, which is quite a well-matured technology in the Azure stack. It's a completely managed version of virtual machines in a sense, so you don't have to worry about any of the updates or any of the security stuff. They just simply keep on updating. One good thing about that is actually that you don't also get any warning when they're actually running a security update or if they shut down the server. In a sense that made us to do better design when we were thinking about how should the services behave when underlying system is going down. We have to really make sure that whatever happens, it should just keep on going on another server. So instead of relying on the fact that all the servers should stay on all the time. We also had different services for analytics. So we have our own analytics stack that uses cloud services and dispatches all the analytics events forward to our sort of a specific cluster that we use. And we use Event Hub in order to gather all those events that are generated for analytics. So Event Hub is also an Azure product or service that is meant to be able to digest millions of messages per second, and then you can have kind of easy tools in order to read them through there. So you can have them persistent there. Therefore, I think the maximum time is around 72 hours or something like that. So you have a little bit of buffer there in order to process all the analytics information and send it forward. And it's kind of a super easy thing to use because there's a lot of boilerplate code that Microsoft provides. So it's basically just file new and you can start reading through Event Hub. Yeah, and then we have a controller that handles all the information. So a lot of time for this need to be put into the way that we actually handle how content is delivered for the games. As we have a dashboard where we'll drive our live events, we need to have a tool that will actually make sure that all necessary pieces of information are provided all the way back to the clients. And we have like other basic stuff built on top of our stack, leaderboards, authentication, social stuff, and so on. And for monitoring, we use a lot of third-party tools, which is part of one of our sort of design principles that are a bit. And of course, like on the gaming side, we use Unity to build our games. So, and how do we actually store our data? On high level, we use a lot of Cosmos DB, which is sort of like a MongoDB, but on steroids, that Microsoft built. It used to be just a document DB. It used to be called document DB when it was only handling basically no SQL queries, but now as Cosmos DB has evolved, it also graph support and things like that, which are pretty handy. And it also supports like geo-replication out of the box. So if we want to replicate our data, it's just a matter of selecting which region we want to put our data in and pressing a button, and it just does everything automatically, which is pretty neat. And we use that for player data, leaderboards, in-app purchases, basically almost everything. And then to actually store the player data, we use Azure Blob Storage, which is just your basic blob storage file system, hosted in cloud. It's super fast. It can scale really well, so nice tool. So maybe on the bit more interesting part is that sort of like what we had to do when we start thinking about what kind of a platform we're building. So firstly, we wanted to create a generic platform, which is always an ambitious goal to do. So no matter what kind of game type our game teams would be developing, we should be able to support them. So all the games should be also able to benefit from all the new features that we introduce into the platform, and that should in general help us to be quicker time to market. And together with that, as we have a common dashboard, we would have common ways of presenting dashboard and tools to our marketing and support. So those are the sort of the goals that we started off with. Then additional design pillars were that we make games, so we want to focus on making games instead of just focusing on creating technology. Secondly, we never want to trust the client, so cheat prevention is very important for us. We have to start from scaling. So when we started building this up, we started off thinking from the get-go, how do we scale things? And then we needed to understand that going live is just the beginning for the journey of the game. So on about how we make games, one of our key principles was use existing services. That's why we choose from the get-go Unity 3D as our gaming engine. To us, it had some great features into it that we really appreciated, which was, of course, like C# for scripting, The community is super strong, all the documentation is great. It's relatively easy to hire people to have previous experience for the engine, and then by now it's basically an industry standard. So that was an easy choice for us. And then another principle was that we don't want to start making our own tools for everything. We don't want to do a log searching tool or monitoring tool or have SMS tool in order to page us if something goes wrong, or create the support tools like these. These can all can be bought from an external provider. We used to have a really nice logging tool in our dashboard that we created up by ourselves, but pretty soon, early on in the early days of the company, people kept on asking requests from me, like, could we get a SQL like search to our logs, or could we get a real-time information, or could we get this and that? So it didn't take me that long to start looking around the internet and figuring out if there would be a service provider that could do that. So we choose log entries for that. So been a great partner so far. In the long run, there's still sort of like, even with silicon toys, there's still a lot of tech to build. Like when you started off, we wanted to make sure we have a scalable system and also secure in a sense that you want to have the trust of the players, that as they're connecting to your service, they're not going to get their information stolen, or we know that there's really hard to somebody come in between and stole any of their information or stole their gaming account. And then also we needed to figure out how do we want to build our global services and chat and leaderboards. There were still like a lot of things that just couldn't be bought out of the package. And for example, for chat, we needed to create a very generic approach, because we didn't want to just create the chat. We wanted to create one tool to sort of be able to distribute messages between as many of clients we want to, and in a predictable manner. We also set to create our own analytics system. We used previously a third-party tool for that, but pretty quickly we figured out that the data that we collect is so valuable for us as a company that keeping that in somebody else's hands and not being exactly sure if you can get it out there or do you have access to it, and not to mention like GDPR and things like that are coming, we decided that it's way more better to have full control on analytics. And then on the live tools, there was just a massive amount to build. We needed to have good tools for player support, even though we were using Helpshift to communicate with the players and have the ticketing system. Still, somehow, when you get a ticket through Helpshift, people needed to be able to actually do something to the player if they had a problem. So we built a tons of like different kind of tools around that. Well, firstly, on this design pillar, like things that we really learned is that selecting the right tool is super tricky, especially when you're thinking about external tools, but also like what tools do you use and what technical solutions you use for creating chats or creating a very generic approach. So it took us quite a lot of time of going back and forward before we came to the conclusion of what we want to do. And then again, the pick your battles kind of a thing is that, for example, for what I was saying about the log managing, is that it doesn't always make any sense to just try to do everything by yourself. It is very much about trying to prevent the situation that you get a fixation that everything needs to be done in-house. And probably the final line is the lesson here that took us the longest time to learn, was that we very much thought that it would be a really good idea to have a very separate tech organization, a very separate server organization that would just create this wonderful service that's generic for everybody, and keep those guys as far away from the actual game development, and just sort of provide a service that the game teams then can handle. It turns out that there's always like a huge gap between those teams, and they're sort of like a void in communication. Recently, we have been moving more in a situation where actually those guys who are developing the server, even though they're doing it in a generic way, they are still injected into the game teams and part of the everyday routines of the game teams, because that's the only way they can really hear and listen what are the game developers themselves, those who are actually writing the client code, really needing, and then what are the designers really thinking about and how they do interact with each other. So moving on, next design pillar, which is never trust the client. So in order to achieve that, you never need to trust the client. We thought of it what we could do. So we came up with very common approach these days is that we will run the game logic on the client and also on the server. So the logic part we basically call model, comes from the MCV kind of thinking of things. And what that made us to do is that we needed to have a deterministic approach to all the information, which sometimes can be a bit tricky. So basically, what is the model? It's basically the game logic that we run on both ends on the client and on the server. And the great thing about that we're running on Unity was that as it is written in C#, we can actually run that exact same C# code on the server side. We're basically sharing a submodule from Git on both ends to run those. To illustrate a bit, so here's sort of the way that we do a data execution model and connection on a high level. So basically, when the client calls the server, it just goes to an init phase and through Traffic Manager and gets an address. Once we have connected a single instance within the cloud service, it will get a specific address back, and for on that words, we can actually establish then persisting WebSocket connection to that very specific instance. So we know it's going to always stay in that very specific instance until the session ends. Now, once the player is loaded into the server, the game logic is basically loaded on the server, and we cache it in order to make sure that we don't have to load it all over again. For example, if there's a short disconnection or some distribution within the network. So once the game logic is loaded on the server side, we do the same thing and we serialize it and send it over to the client. So now we have the same logic and same state running on both ends, so on client and server. So if we want to do any action that would actually change the state of the player, the client will first create a command that will be passed to the game logic. And then the game logic will execute it and do first level of validation that will that command be able to be executed locally. So we do all this we do in asynchronous manner. So we just keep on executing new commands and then we set them in a queue. And once that's done, we can send them over from the queue back to the server. So basically what we do, we just transform that into JSON and send it over to the server. And then the same JSON goes in, it's transformed into a command, and then it's ingested by the game logic on the server side of things. So that way we know if everything is fine. Now, as long as the state of the game logic on client and the server are the same, the execution as their deterministic models, the execution result should be always the same as long as the inputs are the same. So if somebody tries to tamper the values within the command, we will notice that because we would come up with different results, or the results could fail. And if everything is fine, it just returns Boolean basically to the client send, and everything's fine. If it's not, it will the client would know that something is wrong, and it will just reload the state from the server. So it would basically just restart the loading sequence on the server. Forward. There we go. So finally, when the player eventually shuts down the connection or ends the session, we just basically serialize the game logic and store it back in the blobs. So that way, and also in Cosmos DB, because we want to extract some of the fields from the player data to be more searchable in the dashboard. So why did we do it? Well, firstly, we don't need to write any validation code separately on the server side. So once the logic part in the model is written and the commands are written, you do the validation on server and client always the same way. There's no double libraries of code that you need to maintain. If we would run the code, for example, the backend with Java or anything like that, then we would always need to just transform C# into Java. Of course, there are libraries and tools to do that automatically, but their accuracy isn't always 100%, so some really, really neat kind of errors could occur. Asynchronous execution with queue, well, that helps us to keep everything nice and smooth. So for the client, everything is happening asynchronously behind the scenes for most of the time. So we don't have to really wait until the response comes back from the server. So we can just keep on executing because it's deterministic. As long as we execute, everything should just happen the same way. It's super responsive. Of course, the problem is that if there's a very long round trip for the data, it might be that you have a lot of commands in one queue, a lot of commands waiting in queue, and once you send them over in a patch and something goes wrong, you might lose, do a rollback for a little while. But usually that means that it's around rollbacking of information 2 to 3 seconds, which is in our games or most of the games not a critical thing. And of course, now that we have the model and the logic running on the server side, we can actually do hotfixes that we just update the server side of the code, so we can change the logic of the game and do fixes to the logic without actually updating the client side of things. So if we do some sort of mistake, for example, we give too much goods for players through the model or something like that would happen, and then we could just change that on the server side. Of course, the drawback of that could be that every player that tries to abuse that problem or hits that problem would be automatically reloaded, or their game session would automatically be reloaded on the client side, but at least they have still a working game, so we can sort of mitigate the problem. So what did we learn about running deterministic model on both ends? Firstly, Mono and Microsoft don't do everything the same way. So it took us few very long nights to figure out that firstly, and this is dumb to figure it out in such a long session, but it took us quite some time to figure out, okay, it is true that the float numbers don't really work on the platforms the same way, even though, on the specs they would. So we need to create a fixed point calculation for all our calculation on the server side. But then there was another situation which was even more trickier, which was that the lists, if you use the list object on C#, not all of the items were in the same order within the list items, within the list when you added them. So if you add 10 items into a list, you try to pull something out of there, turns out they're not always in the same order, depending on are you on a server or are you on a client. I can tell you it's really hard bug to hunt down. The problem there is that the string hashing is a bit different, so that might cause a situation where when you order things, they go in a different order. We know that there's no magic to deterministic. This goes along, but everybody needs to care about the data. So even though we give the tools or for game developers to actually have commands that they use in order to execute or change the model, there's still like a lot of temptation for people to change the player state or the model state without using commands. So it takes a lot of just teaching people to start understanding that you can only interact with your own game logic through these commands. And then of course, like to care about the data and how much you're using it, or how you're using the data and how you're affecting your state is very important. So if we then go to how we thought about scaling, firstly, it all began with is that you have to scale first you cannot just first do a backend system, especially when you're creating a generic system that could be used by any mobile game that is basically done on Unity and just obeys our interfaces. You have to first think about the scaling in a sense that first you have to figure out how it's going to scale, and then you have to figure out if it's going to work, not another way around. Because if you first start thinking about how it's going to work and how you're going to do it, you're probably going to end up doing solutions that then later on it's going to be really difficult to scale for massive use. So for connectivity, we basically we wanted to make sure that we have enough services available. So how we achieved that, we used Traffic Manager that I mentioned probably earlier on, which is also an Azure service. It's a very sort of easy to use load balancer that you have options of round robin, you have the closest possible endpoint, and then you have a few other options there. But it's sort of like just setting in few settings and then clicking go, very much based on DNS. So through that we can also that when the user is connecting, you get connected to the closest data center. And we wanted to be able to be supporting multiple data centers concurrently, which is another story altogether, how to do that. And then from from Traffic Manager, they will get to the front cloud services. And those front cloud services, the cloud service itself is a collection of virtual machines, what they call instances. And that cloud service has a built-in load balancer, so it will choose from one of the cloud services an instance for that player. And we can have what this enables us, we can have multiple cloud services, which is basically a collection of virtual machines. So we can have I think we had, when we launched the game, we had around 100 cloud services, and underneath each of the cloud services we had 20 servers. So that's 2,000 servers. I think in cores that was around 8,000 cores, just because we had a quad-core computers running in there. So quite a massive setup. So in order to achieve this with cloud services, you need to first connect to the very end instance, and once you get there, you will get a specific address of that very specific instance, and then you can use that address in order to keep the connection alive. And if there's disruption with the connection, you can always try first connecting the very specific instance address, and then keep on doing that until you totally fail, and then you can just restart the whole connection process just by connecting to Traffic Manager. So in order to make sure that the front servers themselves can actually handle all the traffic, we needed to be sure that we cache a lot. So all the players are basically loaded in the memory, so even though the front servers are stateless, in a way they're stateful because we keep the player in memory. And we just put the whole model in the memory. So it's really fast sort of to retrieve the player when a command comes in. It's actually already a up and running object in memory in a dictionary, so there's hardly a faster way you can access in C# at least to an object than actually have it as an instance already up and running. And we keep them until they log off. So what happened there is that as we're working on JSON, we are very CPU bound. That's mainly because we serialize a lot of JSON. Our player JSON sometimes can be up to 4 megabytes, which is quite a lot. Of course, if you need to transfer all the data over to a client, that would take quite some time. We can compress it, but usually what we do is when the player loads their state, we just compare the hashes of the state on the server and client, and we can optimize it in a way. If the client already has the same state as the server, there's no point of moving it over. So in order to achieve all the necessary traffic, we also wanted to make sure that we are partitioned well. So as we store all the JSON in Azure Blob Storage, they have a limitation to only support 20,000 requests per second. I think that is with around 200 kilobytes worth of data. So And we wanted to be able to support like 1 million concurrent users because we didn't know how big the game is going to be, and there was no telling to it when we're working with big licenses like The Walking Dead. And we were launching simultaneously as the new season was starting, and we had a lot of massive TV campaigns and everything going on. So there was no way of knowing us if we would hit what kind of amounts of players we would hit. Of course, we had good guesses, but they were only good guesses. So what we did there is that as there's a limitation of 20,000 requests per second for a Azure blob storage, we created 96 storage accounts and partitioned among those. So we sort of work around the system, and that gives us like a nice amount of concurrency that we can support while storing the player. Secondly, what we wanted to do is that as we're creating a generic platform, we wanted to make sure that we have good enough social features, but we didn't want to lock ourselves into sort of like creating a specific social feature like a guild separately and chat separately, and then we would keep on doing those things forever. Instead, what we actually did is a distributed messaging system that just guarantees the order of the messages, because also our social states are deterministic, which can be tricky, but it also gives you good benefit of people are really hard time to actually cheat on their social information also. So this is basically our setup. What we do is we run always the social model front servers. So when you send a command, that command can then execute a special request saying like send a social command that will be then transferred on the social server. And then when the game developers want, they can actually even within that trigger a situation where they're going to store the current in the storage, so we can replay, basically recreate if necessary all the social states. Then the social server will know which players are actually connected and to which front servers, and it will distribute all the messages in the right order into all the front servers, and then the front servers will then execute it against the social model that is on the front server. And if the social model so wants, it can then send the message back to the client, but they can optimize in a way that if they just don't return anything, nothing is going to ever be sent to the client. It's just going to change the model. So in order to test everything and that everything scales, we wanted to be sure that we have tools for it, and we also wanted to be able to simulate real players. So what we did, we recorded these commands as we're working now with the system that all works around commands. It's relatively easy to just do a playback of these commands and then have some player IDs in order to simulate social features and join of guilds and all that, and some push tokens in order to simulate, let's say, a push token and all that necessary thing. So Visual Studio has a bunch of great tools for that. Visual Studio Online has this basically a load testing harness that you can use. You just basically put a unit test in there, you can send it off to the cloud, and it will spin up instances. And even within those unit tests, you can run things in parallel, so you can really harness the power of one service or one server. So what did we learn? Well, firstly, estimating the load is really hard, and testing is really hard. We actually happened to crash the whole Visual Studio Online loading test harness. I think that was back in 2014 or something like that. They have fixed all those problems by now, but it was early on, and we had a good call with the good friends over at Microsoft, and we were explaining, we were trying to simulate a few million players coming in, and they were like, it wasn't meant for that. Don't do it. Well, we managed to do it. We created our own stuff around it, and now we could actually just rip our own stuff away and just use what Microsoft have, because they have great tools for that. Okay, now the final part is that going live is just at the beginning. We at Next Games often celebrate the moment when we go live with the new game or new update, or we have a build up and running. But it always feels a bit grim when you go and try to remember people that this is just the beginning. Now the actual fun starts when you have to maintain the game that you just created. And there has been a bit of a mind shift, I would say. So if you compared the good old games, they were a bit of different, especially if talking about boxed games. Sort of you in a sense, how you created your code and how you managed your data, for example, it was all about just shipping it, getting to the customer, and then then you're done. You already got your money. Your responsibility ends there, unless you need to patch it. But more or less, you can do a very sort of. You don't have to care about that much about the maintainability of the code. It's all about getting the best performance, getting the best gameplay. But these days, things are different. The games keep on growing all the time. When you launch the game, it's very much just the start of the journey. For example, for us, we are continuously growing. We bring new content for The Walking Dead No Man's Land. We introduced quite a lot of new items throughout these years that we've been live. We have introduced the heroes. We have brought new features. For example, we launched without player versus player feature, and we introduced that later on. All of these kind of features, you have to really think about, like how you're going to arrange your code in a way, and how you're going to develop the game in a way that you don't actually shoot yourself in the foot when you start doing these new things on top of it. And then also, of course, like within the games, you have the community now that you have to work with. You have guilds, you have events, you have all sorts of things. For example, forums. You might be wanting to link forums into the game, and all sorts of things. So it's very much more of a service that just keeps on evolving and keeps on working. And your live operations is one of the, if not the most important part of the team once the game goes live. For us, for example, if you think about, like, we went live around it was 2015 fall, so it's over 2 years ago, and actual game development even didn't take that long. So we have been now more in a period where you're developing things after the actual launch of the game. So in order to support that you can actually have the necessary information available for the game, we had to create a pretty powerful content delivery system. So what we have is we have a dashboard that includes content delivery, A/B testing, segmentation, player support kind of things, that we can then publish all sorts of pieces of information and content to the game. And as this is a generic system, we don't really care, the system itself doesn't really care what is the information that the games need, because the games actually define the content, and we just use that definition in order to populate views that they can just then, as web forms, can fill out and create content for those features. And we have a controller that will handle all of the publishing parts, so it makes sure that the information that is published is in the right place at the right time. And then we can distribute it to CDN or Azure Media Services if those are video clips. So what we have done in the Walking Dead No Man's Land is that every time an episode airs, we have, and usually it airs on Sunday, especially here in US, we have on Monday, we have available content that is relating to the just shown episode a day before. And we also have sneak peeks and special features, video clips that we can show within the game. So we use Azure Media Service in order to show those video clips. And then we use the content delivery system to deliver the new content, so it would be available for the players day after they saw the episode. So you can imagine it's very important for the fan to relate to the game, in a sense that you can see something in an episode a day before, and then later on you can, for example, as they introduced a new character, you can play the new character, or you saw some environment, you can play within that environment, or we have missions in that environment. It's very powerful, that stuff. So what we learned, well, if we could now go back to 2013 when we started to do everything, we would start thinking of operations from day one instead of like just trying to slap them on as we figure out we need them. So and understand better what kind of tools live operations actually need. They need notifications. They need campaign management in order to figure out like how they're going to align all these events. They need segmentation and attribution in order to be driving all these events within the game. So those were basically the basic pillars that we have when we were designing our system. But moving forward, thinking about where do we go from here, as we have a pretty massive tool. It is built on cloud services, which is, it's well matured, let's say that way, as a service on Azure. So what are we going to do next? Firstly, we are in a transition that we are now moving all our services to run on top of Service Fabric, which is a microservice platform. Most of you are probably familiar with the Kubernetes and the likes like that, but this is basically the Microsoft offering. There's a few differences there where Kubernetes can only handle containers. Service Fabric can handle applications, so it can orchestrate applications instead of just containers, which gives you a way better fidelity. You can fit more stuff in one VM when you don't have the overhead of a container. It's not much, but it's still there. It's overhead. So that's definitely one of the sort of future steps that we're taking. Also, it will give us a better support of supporting multiple game versions being live at the same time. We already have that capability, which is really great tool. We noticed that it's very beneficial to actually be able to run two versions simultaneously live. So when you push an update, even though if it's a mandatory update to the users to download on Android or iOS, you could still run with the old version, and just some of the features will be flagged off so they don't get broken. For example, social features. You can imagine there would be problems if you're interacting with the player who has already updated their game and already done migration for their player state. So we might need to need to close like social features from the game client, so they can still keep on playing. They can still keep on achieving what they're trying to achieve within the game, having fun, but they don't have to update on the date that we say they need to. So, for example, here in US, when you have data plans and things like that, you have the option to wait until you are next to a decent Wi-Fi connection, so you can download our game. With Service Fabric, that comes even more easier because all that, like running multiple versions simultaneously in the server backend, is just coming out of the box. It also supports like a graceful failover. So if one of the updates that we put in all of a sudden would go haywire, we could still pull it out and then cancel the update, for example. And we're already running some of our upcoming games on Service Fabric. And just this is like a funny part of that is that we used to have maintenance breaks when we needed to update servers. Now these days, actually the game teams were congratulating us. They said, hey, you didn't need to update your servers for a long time at all. So no, we actually did that already 33 times in a week, but you just don't notice it anymore. So that kind of flexibility is definitely where the future is going on our ends. And also we want to definitely close the feedback loop. So we want to be able to integrate our analytics deeper into our backend. So we just don't want to collect analytics and do reports out of that. Instead, we want to use machine learning tools in order to actually understand what's happening and automatically feed that information back into the game. You can imagine like a situation where you're trying to maximize or trying to improve some part of your game, but it's really hard to find the patterns which will affect it. But if you could do a real-time feedback loop, looking into the data you collect, changing the values and working from there, artificial intelligence is actually way better on that than usually humans are, because humans tend to be biased on some feeling, for example. If you could be like optimizing tutorial, there's like the ever-ending debate on should you have a long tutorial that really keeps you on the rails, or should you have a tutorial that's very open-ended, doesn't really hold your hand that much. There's probably no right answer to it, but with these kind of feedback loops, you could actually be able to serve the best possible solutions for all kind of users. And also what we want to do currently when we're moving forward into our improved system is that we want to abstract the games more. Even though everything in our generic system is built in a way that we just try to move it on the sort of outer rim of the system. I often say that when the game tries to change some of the data, what we want to do, we want to take that command, put it on a long stick, and just try to pull it as long away from us as possible and send it off to another instance of the game logic. But even when you try to do that, when we were building the system, as it was evolved through years, we need to do every now and then cut a corner and do something game specific. So in future, we definitely would like to be more abstract on the game level, so that we have basically a game image package that we can just upload into our servers, and without actually knowing any of the details of the game image package, we could just run it on one of the instances and underneath one of the services.